Okay, so this is going to be an overview of material properties, some safe design concepts, and stress. So for many of you, this will be review, and I'll ask you to come up and lecture about the particular slide. No, I'm just kidding. I'll cover it, but I'll have you guys help me out because I know you guys know some of this stuff or should know some of this stuff. Right? Should know being the key there. So, modulus of elasticity, what's that telling us about a material? My engineering students.
The elastical properties of the material.
Okay. in a circular definition. No, you're dealing with. So modulus elasticity is talking about what? Its ability to resist deformation, right? So it's you could call it stiffness or resistance to deformation, I guess would be the best way to put it. How does that differ from ductility? What's the definition of ductility? Well, how much can it resist? You know, how much does it want to elongate? How much can it bend? Right? Is it before it, or stretch out before it ultimately breaks? Right? Because what's the difference between a brittle material and a ductile material? So right, a brittle material is not good in tension, but a ductile material will be good in tension. Right? Brittle materials are typically much better in compression. So shear strength, we're just dealing with, you know, what the value is for how much force we can put on it before, or how much stress we can put on it before it's going to shear, right? And because we don't have charts that provide us what the yield point is for yielding in shear, we have some approximations, and those are our equations that we use to deal with that. So hardness and machinability, toughness, fatigue strength. What are some of those talking about?
So hardness is inability to penetrate.
Right. So resistance to either abrasion or even deformation, right? Mm-hmm. Okay. What about machinability? That one's easy. Just what it says, right? How well it machines. Yep. Because some materials are pretty easy to machine and some are just a real bear, depending on their properties. You can get steel that has lead in it, so that makes it really easy to machine or turn. If you're dealing with stainless, you have to be careful and with your feeds and speeds, because you can work hard in the material if you're going too fast or even going too slowly. So there's kind of a sweet spot that you want to be in. Otherwise, you just start breaking tooling. What's the other one? Titanium is really a bear to machine because it wants to tear. It doesn't cut off cleanly, or doesn't produce chips like steel or aluminum would. It wants to tear, so it's difficult. Toughness. What do we think about toughness? kind of, well, similar to hardness in the sense that you're looking at, you know, how it absorbs loads, right? Can it absorb an impact? And fatigue strength, come on, piece of cake. We just did this last quarter.
It's like the life cycle of material.
Right, so if you have varying loads, right, if depending, this particular chart speaks to endurance strength, as long as your load is below the endurance line that they have here, and or the number of cycles, if your load goes up and your cycle count goes down, as long as you stay below that, then your part's not going to fail. So in these, aluminum doesn't really have a endurance limit. It just continues to, it'll just eventually fail. It doesn't have a yield point. So creep and relaxation has to do with once it's the material is under load, and then what happens to it after that. Most of the time, this is a function of elevated temperatures and is particularly effective, or plastics are particularly affected by this, not so much the steel and aluminum unless you have you know, fairly elevated temperatures. But your material, if you have a heavy load on it, will tend to kind of shrink in thickness and squish out the sides, shall we say. Or if you have something pressed into a hole, it doesn't maintain that tight fit. It'll begin to shrink and become loose in the hole. So when we're working with our designs and trying to determine what the limit is and where we are, we're always trying to stay in this linear portion of the elastic curve, right? Because we don't want our material to go plastic and change shape. We want it to, when we put a load on it, it might deform slightly, but when we remove the load, we want it to go back to its original shape, right? So this curve is generated with using carbon steel, but in a lab situation that you're not really ever going to see in the real world. Typically, you're going to get to the proportional limit, then it's going to go plastic, and then it'll fail, basically. So, but anyway, we're going to try to stay, or all our design stuff, we want to stay on this linear portion of the curve to make sure that we're not going plastic and failing our part. So stress, P over A should be tattooed on your brain, right? So we're looking at the force over an area and how much stress we're putting into a material. Strain is our change in length over our original length. So when we deform that part, how much strain are we putting into it? And our stress and strain are related, right? If we have strain, then that means we have what? Stress. If we have stress, that means we got strain. Can't have one without the other. So we'll talk about tension, compression, and shear as far as our different types of stress. And we're trying to determine where the highest stress is and make sure that that's within our yield or our elastic curve of our material, or as part of our, we might take that yield limit, put a safety factor on it, and make sure we're below that, right? So that's what we're trying to do when we're doing our analysis. So we'll talk about elements as it relates to finite element analysis, which will be a little bit different than our element that we picture when we're dealing with stress and talking about tension, compression, or shear. But we still, this still has to be part of our thinking when we're looking at our design and what we're trying to come up with, right? And I don't know that, yeah, we're not going to worry too much about that. So, assumptions that we're going to make when we're doing these calculations. And most of this stuff is coming from, way back in 312, right? So it should be stuff that most of you are pretty familiar with. But we do have to remember that when we're dealing with our analog calculations, we are constrained with some of our assumptions. Not so critical when we're dealing with our FEA. So, but when we're making a comparison, we have to do that. So our axial deformation is going to be PL over A as far as analog. When we're dealing with our, I didn't do that. When we're dealing with finite element analysis, many of the times we can equate it to a spring, right? And we'll talk about nodes and elements, and the elements go between the nodes, and we'll treat the elements as a spring, and the nodes are going to move, and they're going to have some deformation, or they're going to change position slightly, but we won't analyze them with PL over AE. We'll use our matrix math to do that. Shear, just the concept of shear, the force over the area, and you have to make sure that you know what your this would be direct shear as opposed to transverse shear, which we won't have to deal with. So this is your shear area for that keyway, because you have a force from the hub and a force from the shaft, and this is where your direct shear is going to happen. So torsional shear stress, the torque, and so yeah, its ability to resist rotation. And your polar moment of inertia will, this, do I have here? Yeah. This will change based on the geometry of your object. Angle of twist, similar to our deformation from PL over AE, we're just dealing with angular this time. Also, I do have transverse shear in here. So when we're dealing with our shear element, where did my shear element go, right? So we have, in order for this to be in equilibrium, if I have shear going in this direction, I have to have shear going in the opposite direction. If I just have those two forces, then it's going to want to rotate. So I have to add some more arrows on here so that now this element is in equilibrium. It's not trying to rotate, it's not translating in any direction, it's just holding still.